Hi, everybody. Welcome. My name's Jennifer Griffith, and I work at NUMOA, which is the Northeast Waste Management Officials Association. And I have the website up here for people that aren't familiar with NUMOA. We are an interstate association of the 6 New England states, New York and New Jersey, so the 8 Northeast states. And we are an association of the solid waste programs, the hazardous waste programs, the pollution prevention and toxics use reduction and those affiliated type of programs, and then also the waste site cleanup programs in those 8 Northeast states. So the states work together for waste site cleanup. The primary priority for them is training. And so that's what we're doing here today. We are holding a series of webinars, of which I think there are 5 right now that have an email's gone out about that are coming up. I'm in the process of getting 7 more put together. So all on PFAS. And the genesis of this was we did hold a conference in April on PFAS for 3 days, 3 days of PFAS for 3 concurrent tracks, sometimes 4 concurrent tracks. So we will be doing that that conference again in 2026. So keep an eye out for that. But I also wanted to just show folks the NUMOA website, because also today's presentation will be a PDF of it will be posted afterwards at some point. And then also, so I want to show you where you can find that. So right now on the NUMOA website, so I just clicked on events, and then we have all the upcoming events. The website is definitely geared towards what's coming up, but you can also look at what's been in the past. So here's the past. So we did hold some webinars on other waste site cleanup topics, vapor intrusion, risk assessment. You can look at those, PDFs of those, and then some solid waste topics. Let's see, here was the conference that we held, so that you can look at that in the agenda. I'm in the process right now of getting all those presentations posted to the agenda, so PDFs of those, so eventually those will be available. And then so you notice I'm scrolling down, so at the, later on will be today's presentation. So right now, today's presentation is, or the event is in the future, but as of tomorrow, it'll be here in the past. So just to let people know where you'll be able to find things in the future. So with that, there are a lot of people joining us today. So we will be doing questions via typing them in. So in your control panel, there is a questions box, and you can type in questions at any point during the webinar. You don't have to wait until the presentations are done, but you type in at any point. I'll be monitoring the questions and I will ask the questions. Also, new this time, NUMOA has not done this before, but hopefully it works. We are doing, we're applying for Massachusetts Licensed Site Professional continuing education credits. So in order to get those credits, people will have to do several things. So one thing you might not know about GoToWebinar is it definitely records when you join and when you leave. So anybody that wants LSP credits needs to stay till the bitter end. Also, it can tell if you're like doing something else on your computer, like if you're checking email or doing some other work. So you really need to have this webinar at the top of your work and not be doing other stuff, because if you do that too much and you get a low score, I'm not going to be able to give you LSP credits. So you need to stay on and keep this at the top. We also had to insert some poll questions into the webinar, and I apologize to everybody else who doesn't want the credits, but it's a way of making sure people are still here and paying attention. So we're going to break 3 times for some poll questions. They should be short, simple ones that shouldn't take very long. So if you want LSP credits, you must answer all the questions. And then another thing you have to do if you want LSP credits is you must type in at least one question during the webinar. So at some point, and hopefully it's related to one of the presentations, but again, just at some point during the one or the other of the presentations, you need to type in a question. And then the last thing is, if you do want the credits, I need to know that. So at some point after the webinar, you need to email me and let me know that you do want the Massachusetts LSP credits. So I think with that, I'm going to start introducing our first presenter. But before I do that, just a reminder again, we are going to post PDFs of the presentations at some point after the webinar. And if you have questions, make sure to type them in. And I'm going to make Linda the presenter, and I'm also going to turn my camera off so you don't bother with me. Okay, so Linda Gaines is an environmental engineer and an environmental health science with EPA in the headquarters office. She has worked on environmental site assessments, water and wastewater work, air permits, and hazardous waste permits. After earning her professional engineer's license, she also earned her PhD focusing on environmental health. She maintains, okay, so I'm seeing your slides, but not in slideshow mode. She maintains EPA's regional screening levels, the RSLs, and is also the Superfund subject matter expert for PFAS. So, Linda.
Hi, everyone. I apologize.
So put it in slideshow mode or whatever so we can
Yeah, that's
see.
what I'm trying to do. And I apologize, but I'm not going to go on webcam even for a minute because my connection had already started to break up before when I first joined. So,
Right,
okay,
great.
hopefully, Jennifer, can you see it now in slideshow mode now?
I can see it and I can hear you. So take it away. Perfect. Thanks.
Perfect. Okay, so let me minimize this real quick. Okay, so hopefully that worked. Did it just go out of slideshow mode?
It did just go out of slideshow mode. And also, Ian, I'm going to mute myself, and Ian, you might want to mute yourself too. Okay, there you go, Linda.
Okay, so when I diminish the control panel, anyway, doesn't matter. Okay, technical difficulties. Okay, well, welcome everyone. Yeah, so some of you know, and I do hope you're not watching this presentation for the third time. So, yeah, so I'm just going to talk about the historical usage of PFAS. And I've sort of broken this up into, so first I want to talk about the uses that probably most people are familiar with. And these are the uses that we know are associated with environmental contamination. And I'm going to spend a little bit more time on the uses that it's just not clear at this point. Okay, so those uses that we know are associated with environmental contamination. Probably the one almost everyone knows of is the firefighting foam, most specifically AFFF, aqueous film forming foam. So it's been used since the 60s. It has PFAS in it. Importantly, in 2017, the DoD changed the mil spec for AFFF. This affected the amount of PFOA and PFAS in AFFF specifically. It didn't affect any other PFAS. One other little tidbit about firefighting foam this is just a strange thing. So I recently became aware, thanks to my friends at the States, that firefighting foam has apparently been sometimes used at avian, like chicken, like I guess, what is it, confined animal feeding operations, specifically for birds, that if you have an outbreak of avian flu, one of the ways to call the infected birds is foam. And it's not clear at this point if AFFF has been used, but I wanted to make people aware of this And I am currently trying to get information from Department of Agriculture about this use. So I wanted to mention that. It's an oddball one and it's not really related to firefighting, but there you go. Okay, so another use many people are probably familiar with is metal plating, especially with chrome plating. PFAS has been used as the wetting agent and mist suppressant for the metal plating. And so, you know, the good thing about it was that this use protect the workers and the environment from chromium exposure. Unfortunately, what it meant was now there was PFAS exposure. PFAS is also used to treat the metal surfaces in metal plating. Textiles, many people are familiar with this. PFAS have been used extensively to coat textiles to allow for the textiles to repel water, oil, and stains. All types of clothing, outerwear, accessories, also particularly like technical textiles that are needed for high temperature and corrosive environments have had this type of a coating. And the fluoropolymers themselves can also be woven to make textiles. And actually, I want to go back to this one for just a second. So this has definitely led to contamination at textile coating operations, the actual facility. Another thing where this is coming in is we know that dry cleaning facilities are associated with PFAS, and it seems to be not from the actual dry cleaning fluid, but it seems to be associated with what they are dry cleaning. In other words, these textiles that have been coated with the PFAS are leading to contamination there. Oh, okay. Another use is paper and cardboard. PFAS, again, similar to textiles, they are used with the paper to provide water and oil resistance for all types of different paper, food and non-food use. In many cases, it's added at the pulp making stage. And I will say the FDA has limited now what types of PFAS, or if any, can be used with food contact paper. Plastics, PFAS are used to make fluoropolymers, in other words, as a processing aid. And then these fluoropolymers can be used in lots of different consumer industrial products. They have a lot of great properties. That's the thing with PFAS, is they provide a lot of great properties for whatever that particular use might be. And again, in this one, that same, similar to like textiles, the high temperatures, the harsh environments, the corrosive environments, the fluoropolymers work really well. Okay, we're going to pause for a poll question. Jennifer, do I need to give up control for you to put the poll in there?
All right, I forgot to unmute myself. I think I have it up, and people can quickly pick the one that Linda just did not talk about. Says it's collecting responses. So if you, especially if you want the LSP credits, you have to answer this question. Other folks, it's optional. So we'll just wait another 1 minute, and then I will close this one, or maybe not even 1 minute. It looks like a lot of people have voted. Just make sure if you want LSP credits that you did vote. All right, I'm going to close this poll. Okay, take it away, Linda.
Okay.
Oh, now we're back. We're back to the beginning, and we're not seeing the slideshow mode either. Sorry. Oh.
Yeah, no, I know. Here we go. Let me see if we can get back there real quick.
There
okay,
we go.
Now are you in slide? Okay.
Yep.
Okay.
We're good.
Perfect. Okay. So let's talk now about the uses where definitely PFAS has been used, but it's just not clear if this is going to lead or has led to environmental contamination. Okay, so PFAS are, good grief, what did I just do? So, sorry guys, it was doing something weird with the screen. Okay, here we go again. So PFAS have been used in electronics. I mean, sort of similar to what I was just referring to. The fluoropolymers are used in cables and wires. PFAS can be used for lubricants and coating the devices. Something that I think is kind of cool, in the upper right hand corner is this photo of, it's a computer server, and the server is actually in a fluid, and the fluid is PFAS, and it's used as the it's used as the heat exchange fluid because servers generate a lot of electricity. And in fact, there was just a news story in the Washington DC area about a server farm that's making lots and lots of noise because of the fans running to cool all those servers. So now they're going to switch for the servers to be in liquid. So I have to wonder if now they're going to, all these servers are now going to be in PFAS. I don't know, but we may be seeing more and more of those uses. Definitely they're used in the semiconductor industry. Again, these same types of properties, the PFAS, they reduce the surface tension, and it helps with all these different uses. Similar to electronics, in photography, lithography, PFAS have been used. It's, these dirt rejectors, they helps with the surface tension, static electricity. So yeah. Cleaning products, lots of different industrial and consumer cleaning products PFAS have been used in. I mean, sometimes it's only, the PFAS is in there, maybe it's only 1%, maybe it's even 0.1%, but it provides these properties that really help the cleaning product do what it's intended to do. And this is particularly true with cleaners for like strong cleaners, for like more industrial type stuff, for cleaning like concrete and masonry and things like this. And then I previously mentioned about dry cleaning. There is a little bit of information about PFAS used in perk replacement systems, but again, the information we have so far where PFAS is associated with dry cleaning operations, it seems to not actually be that fluid. It seems to be what's being dry cleaned. Lots of different coatings, waxes, paints, inks, you name it. PFAS have been used in these. Again, it provides these really great properties. It has to do with leveling, like foaming or not foaming, substrate wetting, things like this. It's been used on glasses and metals as an anti-mist film. I personally wear eyeglasses. I have to wonder if they're coated with PFAS. Pesticides. So PFAS has been used as both the active ingredient in pesticide, like in other words, this is the ingredient that's killing whatever the pesticide is trying to kill. And they've also been used as the inactive ingredient, or the thing that's helping the active ingredient do its job. I do love this photograph I found from Purdue, where on the right it shows how the pesticide, well, in other words, the water is beating up on this leaf, and so if you have a pesticide in there, it's not going to get into the leaf to do what you want it to do. Whereas on the left, the surfactant in it allows it to spread across the leaf and then get into the leaf itself, and that's something PFAS can do. This is the point where those of you who have heard my presentation know I sort of nerd out a little bit, and ask those of you who are old enough to remember the movie The Abyss. Like, I think it's late 80s. Ed Harris, Mary Elizabeth Mastrantonio, I think is her name. Anyway, it's these deep sea oil drillers, and there's this part in the movie where the Navy SEAL talks about when they go diving really, really deep, they don't breathe gas, they breathe a liquid. This becomes sort of a plot point. I just sort of nerd out because that's not complete and utter science fiction. I think the part about humans being able to breathe it is science fiction, but this was an actual, they actually have done these experiments to have animals breathing a liquid, and that liquid is PFAS. It's an emulsion of PFAS, and so it's not that the PFAS are allowing you to, the PFAS are acting as a carrier for oxygen, this highly oxygenated emulsion that allows oxygen to get into your lungs. And yeah, sorry, please excuse the little nerd out on that one. I just think it's kind of cool. This was first researched in the 60s. Those same type of emulsions were then later examined as a substitute blood product. There was a drug, fluoroalkyl, I don't know how to pronounce it, but it was an intravascular perfluorochemical emulsion that was used as, you know, to carry oxygen through the blood. This type of drug was actually, it was also registered in several other countries. So other PFAS have been used have medical uses. There are a couple of compounds that meet most definitions of PFAS that are in fact registered drugs, particularly several inhalation anesthetics. So anyway, yeah, several medicine uses. And of course, well, implant, like the fluoropolymers can be used in implanting devices. Okay, personal care products. I think many people might actually know about this. PFAS are used in emulsifiers, lubricants, for the cosmetics. In other words, to let that cosmetic, let the personal care product do what you need it to do, like the water resistance for the sunscreen. And in fact, there was a report recently out of California about the amount of loading in wastewater of PFAS that may be due to personal care products. Refrigerants, there's a lot of PFAS that are actually used as refrigerants. These are not the PFAS that many people think of, you know, not PFO and not PFAS, though, but these smaller molecules, many of which qualify as PFAS, can be used as refrigerants. Something of note, you know, we first noticed that scientists noted that propellants were causing the ozone to diminish, the ozone layer to diminish. So then we switched to different products that wouldn't cause problems with the ozone layer. Unfortunately, many of those replacements are now powerful greenhouse gases. So then we've been switching to better alternatives, and many of those better alternatives are in fact PFAS. So there you go. But that is a use for these smaller molecules as refrigerants. Finally, okay, PFAS have been used in building and construction. There are several concrete mixtures where the PFAS, they help the concrete do what you want it to do and get where it's supposed to go. Fluoropolymers have been used in construction. I think many people talk, you know, these roofs, and I'm not actually sure if this is a fluoropolymer that's spun or if it's a coating of like fiberglass and such, but these types of tent-like roofs, the PFAS is used for that. Munitions, I think this is one some people may not be aware of. PFAS have been used in munitions since at least the 50s. They're pyrotechnic oxidizers, and they're used in infrared tracking flares. Fun fact, MTV for me used to be, I thought it was music television, but it can mean magnesium Teflon biotin. So it's a composition for energetic material, Teflon, biotin, both being fluoropolymers. And those can be used in those infrared flares and such. Some energetic material itself can also be fluorinated. Also, in sort of what I term to be munitions, a while back, U.S. Fish and Wildlife said, like, you can't use lead in waterfowl shot because it was lead to lead poisoning in the environment. And one of the replacements, so they've allowed for several different replacements of lead, and one of them involves fluoropolymers. Okay, the oil and gas industry, they use surfactants that have or can have PFAS in them to enhance recovery in oil and gas wells. This improves the subterranean wetting, increases foam stability. So just it can be used in these wells. There's a little bit of information about PFAS used as evaporation inhibitors for gasoline. Hydraulic oils, particularly aviation hydraulic fluid, can use PFAS. And yeah, so a couple different uses. The mining industry, there's there's evidence that PFAS has been used as surfactants to enhance metal recovery of ores in different types of metal ores, and then used in the ore flotation process to separate these metal salts. There's also at least a little bit of information about them using PFAS as mist suppressant agents, similar to the way they're used in metal plating operations. I think I probably talked really fast. But so in conclusion, they have been used in a large variety of industries, and lots of industrial and consumer products. You know, importantly, in many of these applications, they may be used in very, very tiny amounts. And then again, as I was sort of speaking to, it's not clear in some of these uses if that's actually leading to environmental contamination. But you know, there's evidence there was use there. But I think part of this is going to be like, how is the waste handled in those types of processes? The DOI, that's a link to the paper I wrote. It is open access, so anyone can go use it and also use it as an aid in case you have insomnia. And I think that's it. So yeah.
Yeah, Linda, you did go very fast through that. So there are a few questions, and I will also make a few comments here. So I think at the beginning of Linda's presentation, she talked about sort of the somewhat well-known uses of PFAS that have resulted in environmental contamination, you know, that a lot of states and areas have. But we will be doing a couple of webinars coming up on some of these other ones. We've got one that's all about ski wax and its contribution to both human exposure, but also environmental contamination. So Linda might have to revise her presentation after that. That will be in October, and but you know, how widespread that is another question. And then also the floor waxes and floor stripping and that sort of thing is, I think, becoming more widely known again as potential environment source of contamination, particularly if you have a septic system, but also if it's going to the wastewater treatment plant. So, and we are going to have another webinar more specific to that in probably in December, so look for those. So I'll just say that about these things. So all these other uses, you know, they can also, like the textile coating, you know, sometimes that contamination results not from the waste management, but just from the air, you know, the air emissions from those processes. So it's not, you know, there's a lot of problems.
I'd like to add on to that, Jennifer. You bring up good points that, like, there's been several studies, you know, where they're looking at dust or air, like airborne, be it, you know, like an actual vapor, or more likely like dust in like houses and in offices, where they're finding PFAS. And there's so many different uses. It's like, okay, is this coming from your stain resistant carpet? Is this coming from the wax that's on your, your hardwood floors or ceramic, in other words, there's so many different uses that it's very difficult to drill down in many cases. Where is this actually coming from? So,
Right.
yeah.
So because as Linda said earlier, they do impart so many useful properties that, we like things. So somebody is asking, and I don't think Linda was going to know the answer to this, and I don't either, but maybe someone that's on here does. Is there a type of textile that is waterproof without the use of PFAS? I mean, there are plastic and rubber, but those don't breathe very well. So, that's oh, yeah.
Yeah, I think my understanding is from conferences that I've been to that, for example, Gore-Tex, supposedly they stopped using PFAS, but I don't know what they've used instead. But yeah, I mean, the main things that are, weatherproof are like vinyl, which, as you said, it does not breathe at all.
Right. So I will say we're going to be doing another webinar. This is another one that will be coming up in October. We'll have Linda back again, where she's going to talk about the various definitions of PFAS, because also we're throwing PFAS out there, but there's a lot of different chemicals in there. So sometimes things might be PFOA or PFOS free, or but maybe not all PFAS free. So that's a whole nother, and it's very hard to know, because a lot of times these things are proprietary ingredients. They're not listed. If I think on an MSDS sheet or whatever, the material safety data sheets, if something is 1% or less, it doesn't have to be listed. And so PFAS, we know the contamination levels that we're concerned with are very low. So it doesn't take a lot of PFAS content for things to potentially cause an issue. So they might not even be listed on an MSDS. So do we know, do you have any generalizations, Linda, about which PFAS tend to be associated with some of these uses?
So in my, if the paper that I published on the historical usage, the one that, it's open access. I'm not making any money off of it. Just want to reassure people, there is, if you look at this, attached to it is supplementary information. It's a spreadsheet. So pull that supplementary information, and the best knowledge that I was able to achieve from, all my different sources, it's in that spread. So it's like broken down in terms of, the rows are like either specific PFAS, like PFOA, or it's categories like perfluorinated carboxylic acid. And then I have information listed, like, are they associated with, electronics? Are they associated with pesticides? So that's the best information I have, which admittedly I wish I had better, but that's at least a start in terms of what I could find linking these different things to their uses.
Great. Well, it sounds like, so the presentation PDF will get posted. Hopefully the link will be live in it to Linda's presentation, and then, or people can Google it and come up with it, and then the spreadsheet will be there. So that sounds like a great resource for people.
If you just, okay, apparently my screen sharing is now paused. I don't know what's going on. I'm sorry, I'm having technical issues, but if you, the last slide, yeah, and you'll get the last, when you get to my slides, the very last one, it says DOI, and then there's like it's like a code. Just, if you just put that code into Google, my paper will pop up.
Okay, so we have a couple more questions and then we'll move on. So can you talk a little bit more about your thought about dry cleaning, and that you think it's mostly associated with actually the laundering of stain resistant clothes and water resistant clothing, and also tablecloths and napkins and all the other stuff that might be treated with PFAS. That it's that, and it's not the dry cleaning process itself.
Yeah, so I was able to find a little bit of information about, like, again, perk replacement systems where they use some PFAS. Now, and the thing is, I don't know how common those replacement systems are, but importantly, the state of Florida did a study, and they, I apologize, I don't have a link to their study, but they apparently like sampled like almost every dry cleaning site they had, found PFAS at like all of them, but were able to determine that it was from what was being dry cleaned, not the actual fluid. Of course, which gives me questions about what is their waste stream treatment process. I don't know how that works. But I will also say something I learned a couple months ago. Long story short, I happened to be sitting next to a medical doctor who works for the fire department of New York City. And we were chatting about PFAS, and he told me that at FDNY, twice a year, every single firefighter's turnout gear gets sent to be professionally cleaned. In other words, because I was asking him about like decon of their equipment. Yeah. And so they send their presumably this is in not like all at once, but in other words, all turnout gear twice a year gets sent to be professionally cleaned, which it didn't occur to me later to ask him, where exactly do you send this stuff to be dry, to be cleaned?
Yeah.
And so presumably this is some sort of like industrial sized dry cleaning facility. I mean, that's the only thing I can come up with. Yeah. And if any of my New York friends are on the line and can find this out, I would love to know. Because in other words, if you have a facility that is dry cleaning firefighter turnout gear, one can only, and you know, be it FDNY, be it for the military, their turnout gear, one can only imagine what the waste stream would have in terms of PFAS.
Right. Okay. So here we'll do one more question, and I can also answer a couple of these other ones. But so with the avian flu and killing the birds, I believe it's used to suffocate them. I guess it takes up the oxygen. But I think people are concerned about the animal welfare or why it would be used. But I think it's a relatively effective.
Yeah. So after I got enough information from my state friends, I was able to track down documentation. It's from, I can share some of this, but I'm still trying to track down from USDA the specific information. They have, if you look on their website, they have information about, okay, if there's an avian flu or some other contagious bird outbreak, what do you do? In other words, you have to, I think the term they use is depopulate. And so they reference, it's actually a veterinary, it's like the, I want to say Association of Veterinarians or something like that. Like, what is the most humane way to depopulate, their term. And yeah, so the foam is one of the ways that's listed. And the idea is you spray this foam, and then apparently like the birds, they can't get oxygen, they all suffocate. I'm not advocating, I'm just reporting what is in this documentation. But the documentation is not, it's the only thing the documentation from the U.S. Department of Agriculture says is water-based foam. Well, AFFF is water-based, but it doesn't clarify anything other. And it does say like as in used in firefighting. So it doesn't specify AFFF. It just now, it's so, I'm still trying to get a contact with USDA to get better information about, did they mean AFFF? And if they did, is there any way they can say, please don't use AFFF? I'm trying to track that down now.
Well, there are a lot of other questions because everybody wants to know about this use or that use. So I think we're going to have to move on from here, though. And
I might be able to respond in the comments while Ian is chatting, but I don't know.
That's true. And also, yeah, you could try doing that, Linda. And then also, here, I'll change the panelist over to Ian and I'll start introducing him in a sec. But so, and the other thing is I will try to get some of these other ones, you know, we are going to have, yes, like surf wax, hockey wax, all kinds of waxes have the potential to have PFAS associated with them. Yeah, the septic system, we're going to touch on that with the December one where we talk about wastewater sources. Yeah, there's a whole bunch of questions that maybe Linda can try to answer to people. There are efforts in states to limit and require labeling of PFAS uses, particularly in consumer products. Alternatives are difficult to find. I'm just trying to really go quick to answer, you know, yeah, non-PFAS alternatives. Sometimes the performance is, you know, not the same. So anyway, we're going to move on, and thank you so much to everybody for paying attention. So let's see, what are we doing? Okay, so Ian Ross, our next presenter. He is the global PFAS practice leader. Oops, I got to also unmute him because then he's self-muted and muted by the organizer. Okay, there we go. Okay. Ian Ross is the global practice lead at CDM Smith and is a visiting professor at Manchester Metropolitan University in the UK, although he has recently relocated himself and now lives and works at the San Francisco office of CDM Smith. He has over 30 years of experience in the environmental impact of foreign xenobiotics and is focused solely on PFAS management for the past 10 years in a global role. So he's written over 100 articles, academic publications, book chapters on PFAS, including the 204-page chapter on PFAS in the Emerging Contaminants Handbook. So before he starts, though, I'm going to do this other poll real quick. And people, especially if you want the LSP credits, you got to vote. Where does Ian Ross work? I just mentioned that. People can pick it. Some people are just picking random things, which is fine, but most people are picking the correct one. Let's just wait for a few more people to vote. And then I will end it and then we can have Ian start. Okay, I'm going to close this poll. Thank you, everybody. He does work at CDM Smith. Okay, with that, Ian, it should work. Take it away. Oh, you are muted, though. Self-muted, it says. Oh, and muted by the organizer. Oh, boy. Okay, hang on.
That's better.
Okay, there you go.
Thank you.
Should work.
Yeah, hopefully you can hear me and see the screen.
Yes, I can hear you and see the screen. So take it away.
So I'm going to talk about the diversity of PFAS and the propensity of some PFAS to naturally transform into others. So as we run through this, what I'm going to try and talk about some of the characteristics that define what a PFAS is, and that's not necessarily the same depending on where you are in the world. The central tenet of PFAS is there's some transformation occurring, and the dead-end daughter products of this transformation, which I'll run into, are called fluoroalkyl acids. And these tend to include things like PFOA, PFOS, PFHXA, etc. And then we'll talk about what's in many commercial products, which are termed precursors. And these are naturally attacked by microbes in the environment and are converted to what's more commonly regulated, like the fluoroalkyl acids. I'll talk a little bit about manufacturing processes as opposed to specific products, then some generalizations about what PFAS are in products, and then some of the common chemical analytical methods to detect what's currently regulated, what's actually there, and how you might go about finding out where the PFAS that are regulated that you've detected come from, using things like total oxidizable precursor assay or high resolution mass spectrometry and nuclear magnetic resonance, which give you an idea of the sort of forensics potential to look for a wider range of PFAS to work out, well, where does my PFOA in this drinking water well come from? Can we find any other PFAS there that will take you to a source of that product, because you find some sort of more weird and wonderful PFAS in the water as well. So PFAS exhibit multiple properties. Generally, they've been classed as containing saturated carbon-fluorine bonds, so carbons that are saturated with fluorine. But adding more than one fluorine to a carbon tends to impart extreme environmental persistence and stability. So this is a central reason why we're seeing some parts of the world regulate PFAS based upon the presence of a CF2 or a CF3, but it does depend where you are as to how you define PFAS. Some can be highly mobile in the environment and some can be less mobile. I'd say the ones we're currently regulating, things like PFOA, PFOS, PFHXS can be pretty mobile in the environment, but then some of their precursors can be much less mobile and can stay in soil, say, for decades, sometimes going unnoticed. Some PFAS bioaccumulate, meaning the organism contains more than is around it, like if it's in, let's say, a surface water, there can be significantly more in the fish than in the surface water itself. Or in humans, we tend to reabsorb PFAS as we bring them back in our renal systems, meaning they accumulate in us, much more than cats, dogs, monkeys, etc. as well. So it's all down on excretion rates, and this comes into long and short chain, as the long chains are those that concentrate more and bioaccumulate up the food chain, and the shorter chains are more easily excreted. In terms of toxicology, there's a lot more coming out sort of every week in terms of understanding of multiple different types of PFAS and their toxic nature and the mechanism by which they act. So this is a moving target which is impacting regulatory standards. And then for some of the PFAS we're looking at the moment, they've been used in firefighting foams as fluorosurfactants. That imparts specific properties where they tend to stick on surfaces, move to the air-water interface, be retained on surfaces, they're surface active. We're seeing that fluorosurfactants have been published throughout, like more journals in the chemical engineering sector since the 80s is forming pretty stable liquid crystalline structures. So we're seeing this inside fire suppression systems, and we're evaluating the surface of concrete to see if there are reasons why there are more solid phases of PFAS sticking there. So a few very strange sort of behavioral properties of PFAS when you add all this up. So to break them down into different types, you can group them with the polyfluoroalkyl and the perfluoroalkyl to start with. And the perfluoroalkyl tend to be those that don't have additional carbons on the structure, we have hydrogens or other structural features there. And these tend to be the persistent type that are going to remain indefinitely in the environment and are generally untouched by microbes in terms of them breaking down and don't really suffer abiotic transformation in the environment. But the other ones are the polyfluoroalkyl substances, and on the end of this green area of this molecule here, which is the perfluorinated tail, we see all these white atoms, which are hydrogens and some sulfur, and this defines the molecule as being polyfluorinated. But these tend to transform naturally in the environment, or when you use chemical oxidants, say you're using ozone for treatment of water. If it's an active aerobic system, like an aerobic sludge plant, these precursors can be mobile, they can come into wastewater treatment plants, and they convert to the perfluoroalkyl PFAS. So sometimes more PFAS can be measured coming out of sewage treatment plants because you're only looking for like a few analytes which tend to be perfluorinated and not looking for the precursors. So when we look at the perfluoroalkyl acids, these are things like PFOS, PFBS for the sulfonates, PFHXS. We're describing these as being more like stone arrowheads. And I'll move on to the rest of the arrow. But these persist indefinitely in the environment, as if you've lost an arrowhead in a battle in sort of 8000 BC, you'll still find the arrowhead there. And the longer chain ones I'm trying to show as having barbs on them, indicating they're going to stay in your flesh. If you're shot by an arrow like PFBS, it's easy to pull that arrow out, but these barbed ones are more difficult, and they're like retained much more in higher organisms. So PFOA, PFHXS, PFOS, PFNA, etc., and the longer chain derivatives here, these are all long chain, and they are more difficult to remove from generally mammals, higher organisms. They're more sort of excreted over longer time periods when the exposure has been removed. PFOS, PFOA, you've got about a half-life of 5 years, and PFHXS is 9 or 10. So about half of this will come out of your body over time when you've been taken off the exposure source. These other ones, yeah, they're far more mobile in the environment. They may be more commonly found in drinking water in some places because they travel much further, but you can excrete them on a daily basis. But then if they're also in your drinking water, you're topping them up on a daily basis as well, or if they're in foods, etc. So you get a steady state of these being formed, but we tend to see lower regulatory thresholds for the ones on the right, as opposed to the bioaccumulative ones on the left. When we talk about surfactants, you need like 4 perfluoroalkyl carbons to be a surfactant. So PFBS is still a surfactant, but when we look at PFBA, it isn't. And there are more than these as well. There are perfluorophosphonic and phosphinic acids, which aren't currently facing that much regulatory attention, but they are used in many products, like some examples of paints, etc., that contain other perfluoroalkyl acids. And then strictly speaking, these ethers like Gen X would be a perfluoroalkyl acid as well, as they don't generally transform in the environment, and they're fully fluorinated without hydrogens on the molecule. So the bigger group of PFAS that are out there are called polyfluoroalkyl substances or precursors, because in the environment they form these perfluoroalkyl acids as dead-end daughter products. We have some volatile PFAS like these fluorotelem alcohols. They evaporate off. UV light can hit them in the environment, or some ozone. They get transformed abiotically to PFOA. This is much more water soluble, so will come down in rain. So we have the potential for widespread distribution of PFAS as a result of some volatile precursors. Then in firefighting foams, we also have molecules that are great surfactants, but they tend not to be detectable using conventional means, and they dominate what's in firefighting foams, but they can also be positively charged and cationic, like this one in the middle here. That means they're going to stick in the fire training area far more and slowly transform to form things like PFHXA from this C6 molecule, or PFOA from this one. So these precursors can be mobile. In some firefighting foams, they tend to be more positively charged, meaning they stay in the source. But we are finding they're moving around in addition to the regulated PFAS. So there can be a lot more PFAS out there, which I'll show some examples of. So to try and make this more simplistic in terms of explaining precursor transformation, if you think there was a battle in 8000 BC, and I think the origins of the stone arrowhead leads to Northern Africa, which is about the period of time when people started manufacturing stone arrowheads, you can still find these where they've been used in battles or in manufacturing facilities from that sort of period of time. I wouldn't necessarily call it a facility, but where people have made stone arrowheads. If this falls to ground, this wooden arrow shaft is going to degrade over time. I mean, microbes will attack this, and lignin is attacked especially by fungus. And it's the same with this molecule. You've got a persistent part here that's going to remain persistent indefinitely, like the stone arrowhead. But you've got these other bits that microbes want to chew on. So the ammonia here, or the hydrogen, that's a nitrogen source. We need a little bit of sulfur. We definitely need hydrogen. That's going to power a lot of metabolism. So bugs will attack this part of the molecule, but they'll spit this bit out. And that will mean that this is a PFOA precursor. So this is dominantly what's in products like firefighting foams. And these tend to be proprietary molecules. Sometimes they can be patented, sold by different companies to others to put into firefighting foam or multiple other products. But I think that the central point is here really to pick all the PFAS up, including the precursors, you would need to move beyond the target list of analytes like USEPA 1633, which just has some of the arrowheads in it generally, and a few broken arrows, we could say, like 6,2-FTS, which are partial transformation products. The other factor with the precursors is they tend to be, well, they've been shown to be significantly more toxic. They go through reactive intermediates that create unsaturated aldehydes, potentially, which are highly reactive and likely to be more carcinogenic, like acrolein in cigarette smoke. So we see some publications showing the precursors can be 10,000 times more toxic, like acute toxicity to aquatic species than the fluoroalkyl acids. So we're seeing more focus on exposure to these, which I'll run into. So moving on, when we look at manufacture of PFAS, there are three main methods out there, but there are also many other for other types of PFAS. Electrochemical fluorination is what was used by 3M, and it was licensed to many others to make things like PFOS, but also they made PFOA. Now, this process tends to create a mixture of branched and straight chain isomers, meaning these chains can have branches coming off, and like that can be an indication of this manufacturing process. So for PFOS, it was about 30% branched. For PFOA, it was about 22% branched. So when you start to see lots of branching, you could say, well, it's probably come from an electrochemical fluorination process. But there are also lots of precursors to PFOS in here and PFOA, and these are in different products. And these tend to be called sulfonamides or perfluoroalkyl sulfonamides. So these are a class of precursors. Then the other method that was developed by multiple others, including DuPont, was the fluorotelomerization, which tends to make dominantly straight chain isomers and was used to make carboxylates like PFOA. It wasn't used generally to make sulfonates and sulfonamides like PFOS. So this is a way you can tell between the manufacturing process. So when you see dominantly straight chain isomers, that can be an indication of fluorotelomerization. But there are also some manufacturing processes where they add branched ingredients, and you can have isopropyl isomers. So I wouldn't say it's completely definitive that fluorotelomerization as a process doesn't create branched, because some manufacturing, especially in Japan, seems to make well 100% branched. So you would need to dig in a little bit deeper when you're assessing the difference here. So the more modern PFAS out there, like Gen X and perfluoroalkyl ethers, Adona, they tend to have oxygen in the chains, and this doesn't really impart any increased biodegradation, but this is manufactured by a different process as well. So we have up here in the Emerging Contaminant Handbook some common intermediates and processes by where you start with different materials here, and these three processes are shown to go through to make multiple types of end products, which are then used in multiple types of applications. So yeah, please feel free to have a look at this book chapter. There's quite a lot of information in there. So moving on to foams, if we look at the 3M light water foam from some publications by Jennifer Field, we see over time it was dominantly PFOS, but then they brought in these precursors here. So these are precursors to PFHXS generally, and these tend to hang around in soils because they're positively charged. So there have only been, I suppose, a few very limited early foams, and maybe more recently foams of very limited number that don't contain precursors. Dominantly, foams contain precursors and not what's regulated and not what we're looking for with chemical analysis. So the more modern foams from another publication by Jennifer Field, really demonstrating that it's a mishmash where you see something like 8,2-FTT-AOS. That is just a precursor dominantly to PFOA. It's got 8 carbons that contain fully fluorinated and 2 carbons that contain carbon to hydrogen bonds, then other functional groups on the end, so a bit like this one up here. But these generally aren't being assessed when we're doing environmental assessments, and they can hang around in soils for quite a long time and be missed potentially in environmental investigations. So there's some examples where you're using non-target methods, which I'll get into, and you can actually find a source zone that's loaded with these molecules that you would have missed. So your conceptual site model for this would be wrong without actually looking for what's in the firefighting foams. You would have not identified source zones. So the point with these, I mean, if we look at transformation pathways and the arrow analogy, we see C6 foams containing things like 6,2-FT-SAS or 8,2-FT-AOS here. These transform through to create things like 6,2 and 8,2-FTS, but when you get to breaking this down to the dead end daughters, which persist indefinitely, there can also be a little bit of chain shortening where you can end up with some shorter chains coming out as well. So you can get a spectrum of chain length. So you might have a bit of PFPEA, etc., coming from this C6 foam, but dominantly it's PFHXA. And then the C8 foam, yeah, can form PFOA, but the C6 foam can't get any longer, so it shouldn't be able to transform to PFOA. So in terms of the speed at which this happens, it can be pretty slow. If we look at all these different examples of different precursors that are going through like wastewater treatment, I mean, you start looking at the time over which it takes 90 days. We've only got like 8% transformation of the parent here. So these precursors can be pretty mobile, aren't necessarily transformed that well in sewage sludge, activated sludge or soils. So that means they can potentially be getting to receptors, but that will be dominantly the anionic ones as opposed to the positively charged cationic ones, which tend to stay stuck in soil. Then to try and sum this up, I think we're saying we've got a lot of these precursors out there that have been termed dark matter, as it's sort of stuff we're not measuring, like the mass of the universe that's unknown. They transform through common intermediates. Some of these can be measured and some of them can't, where we can measure 8,2-FTS, but we can't measure this one here. So they'll be funneling through to more common intermediates and eventually will form the fluoroalkyl acids like PFOS, PFOA here at the end. But these are all common intermediates from multiple types of precursors. So depending on the sort of manufacturing process, you'd need to be looking up here at these precursors to work out what type of manufacturing formed them. Just looking at the fluoroalkyl acids may not necessarily tell you where they came from, which manufacturing site. So there's a lot more value in looking at these proprietary product molecules up here to work out where your mass is coming from and what kind of source is there. So there are only, I think, one main polyfluoroalkyl substance under regulatory scrutiny at the moment. That's US EPA asking for some toxicological work on 6,2-F-tab. And this was a molecule put into firefighting foams like C6 foams by some manufacturers. And it's also been found coming out of sewage treatment plants at, I think it was 6.5 ppb here in the UK. So this is certainly mobile in some places where the geology allows this to move around and not get biotransformed that quickly in like wastewater treatment plants. So this can be a dominant analyte that can go unmeasured. So California's brought out a term broad spectrum PFAS to do the testing, and I thought that as a good analogy to a spectrum in a rainbow, where we've got lots of precursors here which are in the dark here as they're not generally measured, but as we look across all the different types of PFAS, we've got the longer chains here, like PFNA, PFOS, etc. We move into these ethers which have oxygens in here as well, and we've got some cyclic PFAS that are used in multiple applications like aviation hydraulic fluids or metal plating, so they're called PFECHS. We've got the short chains, which are like C4, like PFBA. But we've also got these ultra short chains, which are by far the most prolific at the highest concentrations around in water. And a recent publication showing like 2/3 of the exposure of the US population was coming from ultra shorts. But I'll be talking about those in another presentation. So just to say, there are a lot of PFAS out there when you start looking at the wide range. Some publications now listing over 7 million molecules as part of the PFAS family. So we can make some generalizations about certain analytes and certain PFAS that come from specific applications. For example, paper and food packaging, you tend to find these phosphate diesters here, and that's this molecule here that's got this phosphate in the middle. So this is something that forensically could be associated with some kind of paper surface coating more generally. And you have multiple types of these phosphate diesters or phossies. But when you look at things like firefighting foam, yeah, PFOS was used there, but also metal plating since the 1950s, before firefighting foams contained PFOS. They were used in metal plating. Then we find 6,2-FTS being used as a replacement, but usually in foams it's 6,2-FTS precursors, not 6,2-FTS, something like 6,2-FTAB. And then these anaerobic products, these partial degradation products, some of these have been much more highly toxic. They're generally also formed if there's anaerobic conditions in the groundwater. So you can find this 5,3-FTCA or 5,3 acid coming out of landfills because it's anaerobic, but that's also potentially coming out of firefighting if there's a lot of hydrocarbons there that makes the conditions in the ground anaerobic as well. So there are some specific PFAS that are associated with products, but also you would need to go into like a patent database and look at the precursors to work out if you can definitively say whose PFAS is whose, and use more advanced chemical analysis, which I'm going to dive into. So chemical analysis, I think the iceberg analogy is still relevant in that we have all these target methods. Some labs now globally have got a list of 200 different targets they're offering. So you can get the concentration of 200 individual PFAS quantitatively. But that's still the tip of the iceberg because the vast majority of those won't be the precursors used in bulk products. You're used in products in bulk, say like firefighting foam that were thrown on the ground repeatedly in a dispersive activity. So we have multiple analytical methods like 1633 at the moment with 40 PFAS on, and it's certainly picking up some PFAS, but by means not all that are there. And it may not really produce a psychoceptual model, say, of a fire training area or a base that really is accurate just by using this. So the other PFAS below the ice are these proprietary molecules with other functional groups on, that things like NC6, C8, and fluoroalkyl firefighting foams. And to assess their concentrations, you would move into what's termed non-target chemical analysis, which gives you various degrees of certainty and confidence in qualifying what you found and quantifying what's there. So I'm going to run through these in a little bit of detail. Got top assay AOF, which is a combustion ion chromatography, and I'll talk a little bit about high resolution mass spectrometry and NMR. So this method has been sort of adopted by US EPA with a method 1621 for a derivative of it called adsorbable organic fluorine. Basically, you take a sample, you put it in a ceramic boat, and you burn it, and the fluorine coming off as hydrogen fluoride is measured as it's absorbed in this impinger, converted to fluoride, and then that's analyzed by ion chromatography. And usually, I mean, many labs are getting to about a ppb, but there's some labs like Bureau Veritas in Canada can get to 0.4 ppb on AOF. So it's not down to the drinking water standards, but it's getting there. There are other methods where, well, it depends on how you introduce your samples. The AOF uses an activated carbon cartridge to pre-concentrate a liquid sample. It then incinerates that activated carbon and sees what fluorine's coming off, and you should also get about an understanding of the fluoride in the water as well. The TOF puts the whole sample in there and burns it, but its detection limits are much higher generally. And the EOF is a liquid extraction of a solid phase extraction cartridge, which can get to lower limits and capture potentially more PFAS. So this is a method that just gives you total fluorine coming from organics. So you may pick up all sorts of molecules out there that aren't PFAS as well, in that if you've got a single fluorine in an organic, this may be picked up here and give you a false positive of total PFAS. But then that also depends on which derivative, what your definition of PFAS is. So top assay came out, I think it's 2012 first, and then another paper in 2013. This is a way of mimicking what's happening with the biology using chemical oxidants to some extent, where you you burn off these tails as opposed to letting the bugs degrade them in the ground if this is lost like thousands of years ago. And you end up with a perfluoroalkyl acid. It may not be exactly the same perfluoroalkyl acid that the biology creates, but you get similar chain shortening. But the point being that if you use conventional chemical analysis using these targets, like from US EPA 533, 537, or 1633, you won't tend to find the precursors that are in the firefighting foams if we look at analysis here. You will find from the old 3M foams, yeah, some PFAS is there. But then you oxidize what's there, you burn off these tails, and then you look again, you can see, well, actually there's all these PFAS we couldn't see because we didn't have the analytical standards and we couldn't measure them. But we know that these fluoroalkyl acids are there. So the 3M product here, there's a lot more PFH excess has turned up, and you see for the fluorotelmer foams, you can actually see if they contain PFOS, PFOA, etc. So, or precursors to PFOS or PFOA. But I mean, generally what we're seeing here is also the complexity is that you see carboxylates coming out the other end, which I'm going to explain in a bit more detail because this does become complicated. As what you can do here is visualize the proprietary precursors that you can't measure. So you can get a reasonably accurate concentration of the amount of PFOA precursor in a foam or in the soil as a result of using top assay, which can help you determine whether it's a C6 or a C8 foam, or determine if the soil is highly contaminated. So top assay, as I said, what we're saying, it's analogous to throwing the arrows on a fire and then looking for what we can actually detect afterwards to try and explain it. But we won't be able to see these arrows because we don't have analytical standards for them. But you can detect the arrowheads because we know how to detect those. So you convert one to the other quickly, then you pick up what's here. Now this is where it gets even more complicated in that the precursors in the 3M products, the sulfonamides, by chemical oxidation, they tend to form things like PFOA, PFHXA, these carboxylates. But the biology turns them into the sulfonates. So what we tend to do is look at the branched chain after oxidation to determine, well, is there a percentage there that we can say is really PFH excess? Because you'll be getting PFHXA. And if you look at the branched, you can do a rough back calculation to say, well, is that really PFH excess? And the importance is PFH excess is regulated, it's long chain, and it's bioaccumulative, whereas PFHXA is less regulated at the moment and it's not bioaccumulative. So with the fluorotelmers, you also get this chain shortening that the biology does, and you get carboxylates. And we've recently been adapting top assay to get less chain shortening, which I'll move into. And apologies, this is somewhat complicated with the chemistry, and this is the simplest way I've tried to explain it. The point being, with top assay, from a foam loss in Australia several years ago, with Cleans and DHP, had a look at top assay in the surface water and found, okay, this is what conventional analysis will find us in the water, but actually the top assay is finding up to 276 times more mass because the surface water is loaded with precursors. And then when we try and do some visualization of the PFAS in like a radar plot, you can see for the same sample, this is what the standard analysis will show. There's a bit of 6,2-FTS, but then when we oxidize the sample, all that 6,2-FTS should have gone because its tail's been burned off, and you end up seeing, well, it's converted to PFHXA, but there's much higher concentration in here of these terminal products. It can be important to get a good lab that knows what they're doing on top assay, as you can undercook or overcook it. If the pH shoots down, you can start to break carboxylates down. And so we wrote some guidance on this. Well, Erica Haupt led this a few years ago. I can send that out if anyone wants it. We tend to provide it to labs as data quality objectives. If you've got a lot of other organics in there, you can also undercook top assay. So all the 6,2-FTS and the FOSSA should have gone. So it's important to understand how top assay works and make sure the data you're getting from the lab is actually credible. Because if there's still a lot of 6,2-FTS left after top assay, it hasn't worked. And if there are less carboxylates after top assay than before, it hasn't worked. And maybe they're undercooked or overcooked it. So we started working with ALS on this in 2014, and we're the first to commercially use top assay. So got into quite a lot of the detail of how it works and found labs that can actually deliver this, provide credible data. So some of the output, you can start to say, yeah, you could indicate after top assay here on the same sample, there's a lot more PFAS mass there. Same here. I think you can also get an idea on the scale and look at the different types of PFAS in here. And you can use it to confirm you've captured everything. So it has multiple types of uses. And I think mainly it's there as a tool that allows you to really get a picture of where the PFAS are. When foam's being sprayed on the ground, there may be significant precursor mass, like that's like 100 times more than what we're actually detecting when we're doing conventional analysis, and this enables you to visualize and work out where source zones are. So some of the recent publications I've been involved in, and Dave Sedlak's been doing, really enhancing top assay, looking at linear and branch ratios, as I've discussed earlier. This new UV method is going to be commercialized in the next year or so, and this gives less chain shortening as you get from the conventional method, where you use heat and high pH. So this is also a lot quicker and gives you more credible results. And then the stuff we've just been publishing is on getting top assay to work in difficult matrices like firefighting foams using a hydrogen peroxide UV as well, which enables you to really work out if you've got a C8 or a C6 foam more accurately by combining this method with the UV hydrogen peroxide pre-stage with the UV sulfide digest. So I think the tools we're using more commonly for forensics to work out where PFAS are and what they are is a combination of high resolution mass spectrometry, which gives you the identity pretty accurately of the precursor, because it gets the molecular weight 4 or 5 decimal places of an atomic mass unit for the Dalton. And then the software can back calculate from the parent ion and also lots of fragments of it to predict with various degrees of confidence what the actual parent molecule is. And then that can be used to say, well, this definitely came from a metal plating facility, or was coming out of a paper milling plant, for example. So this is a pretty powerful tool, but we're finding it's even more powerful when we combine 19F fluorine NMR, which gives us the vicinity of the fluorine, well, what surrounds the fluorine in a molecule. So for example, if we know the fluorines are next to a carbon double bond like this, well, the carbonyl group, that gives us a certain peak here, and you can identify the nature of each PFAS. So these two methods in combination are really useful for really determining what's there and giving you an understanding of the nature of the precursors in a sample. So an example of some of this data is what's coming out of a wastewater treatment plant in the UK. They've done estimated concentrations here with high-res mass spec. But as you see, you get a very accurate mass of the molecule. The software then can start to predict what that is. And they're finding the highest concentration is this 6,2F tab, which is not regulated. And then 6,2FTS, which is now on US EPA 1633, but we don't have regulatory standards in drinking water. And then you start to see some more molecules down here, like things that are associated with certain products. And you can start to dive into each individual component and build up a picture of where these came from as a result of them being specific or patented by certain companies. And the grayed out ones here are ones that are in the UK aren't currently suffering regulations. There are analytical standards in the UK now for 6,2F tab. It's going to get a drinking water standard because it's turning up in drinking water supplies at PPB levels. So it is a complicated topic. I've tried to make it as simple as possible. I'd say this is a useful publication we've just put out to go to on the implications of grouping when we've got such a large number of molecules. How do we try and pragmatically assess what to focus on? And I'd say that the main point is that these polyfluoroalkyl substances, these precursors, are dominant ones in most commercial products. They tend to go undetected using conventional methods like 1633. They are precursors to what we're looking for in 1633, or some of the ones we're looking for. Precursor transformation, yeah, it's difficult to predict. Certainly aerobic environments provide faster rates. But in terms of finding everything there and working out the objective of why you want to look for more PFAS, there are multiple analytical methods out there that give you the ability to work out where the PFAS are coming from, or to detect additional PFAS beyond those that are currently regulated. So you can really work out where to use this, depends on what the objective of the project is, as to why you would want to look for PFAS that aren't regulated at this point in time, maybe before they are regulated, which seems somewhat inevitable. So the poll question is, which chemical analytical method will allow detection of PFAS in firefighting foams? So you have 4 answers, and I think Jennifer's going to share something to enable people to vote.
Yes, I did. I think when you're a panelist, you don't get the poll, but yes, people are voting. And yeah, for my purposes, it doesn't really matter if people vote for the correct one or not, but I think people are interested in hearing after we close the poll in a minute, which is the correct answer, but don't say it yet, Ian. So that was a lot of information. We do have some questions that have come in, and it looks like enough people have voted. I'm going to close that. Ian, please talk to us about which is the correct and why.
So the precursors that are in firefighting foam are only really detectable from the host of analytical methods I put in here. It's B. Top assay and AOF can give you some reflection of what's actually there, whereas USEPA 1633 and 537 just have a number of the fluoroalkyl acids, like the arrowheads, and not the intact arrows. So B is correct.
Okay, so not that many people actually picked that. So,
oh no.
But that's okay for people that want the credit. So, that was the end of Ian's presentation, and I think it's very helpful for me because I'm always thinking, did we phase out the use of PFOA and PFAS? So why are they still showing up a lot? And I think it's because, well, some precursors can transform into them. So that's why we still keep finding them in, like in wastewater or something, because, aren't we not using them anymore? But they're still showing up.
They've just been used so much. I think that's part of the issue.
So here's a question. Is it appropriate to conclude that precursor transformation is generally in aerobic conditions? Like, is stuff happening in anaerobic conditions as well, or mostly aerobic?
Yeah, things are happening anaerobically, but you get dead end daughter products like these unsaturated aldehydes, which can be very toxic. So the typical transformation products under aerobic environments are the fluorotelomere carboxylic acids. That's the dominant PFAS that's usually in landfill leachate, is the 5,3 acid. So I'd say it's more slow under anaerobic conditions and incomplete, and generates things which tend to be more toxic.
Anaerobic generates more toxic things?
Well, the 5,3 acid and these fluorotelomere unsaturated carboxylic acids, these are sometimes transient intermediates, but there's some publications from 2007 by Phillips which showed these intermediates are 10,000 times more toxic than the perfluoroalkyl acids. So that's just so far acute toxicity to aquatic species, indicating, that there are things out there that are orders of magnitude more toxic than the ones we're currently regulating.
Okay. So can you talk more about transformation at wastewater treatment plants? I think people are somewhat concerned because they might just be using 1633 and, it could be missing so much, it seems like, maybe.
Yeah, I think it depends what your objective is in terms of complying with regulations. But yeah, this is what can come out of wastewater treatment plants. But you tend to have quite a lot. You can have a lot more perfluoroalkyl acids like dead end daughters coming out. And I'll go back to the slide which showed the percentage removal. Let's just see which one that is up here. I can't remember where I showed this. I think it was that far. There, that's better. So this is the precursor that they tested, that these aren't generally being assessed as part of any sort of analytical suite. But if you look at, so this phosphate diester, what we're finding with these PAPs and the DIPAPs, they can be quite dominant in wastewater treatment systems as they enter attached to particles. There was some evidence of PFAS being associated with toilet paper, some publications from the Bowden lab in Florida. And these tend not to be highly soluble. They're attached to particles that come into sewage treatment. They then get through sewage treatment, get into the biosolids and get spread on land, and then they get converted to things like PFOA or PFHXA. So they're not transformed particularly quickly and they can be difficult to find, but they do end up on cropland where over time they will form PFOA, PFHXA, or the older ones will make PFOS, PFHXS. I'd say that you'll get some nibbling away under aerobic and anaerobic conditions in wastewater treatment. You can get some effective removal. We're looking at aerosolization to remove PFAS in wastewater treatment plants, and some of the anaerobic digestion reject-like liquors can be a place to remove PFAS because you have very high concentrations there. So it gets more complex when you have so many molecules coming in that then tend to concentrate in different parts of a wastewater treatment plant. And we can certainly talk at much more length about exactly what's going on, but it is complicated.
Yeah, because I don't think wastewater treatment plants keep anything for 90 days. I mean, the stuff goes in and out much quicker than that.
Yeah. So you may have some precursor transformation, but the majority may be going through.
Right. And so something could test okay for the regulated stuff in biosolids, but then when you use it later, it could not be okay.
Yeah, depending on when regulations start advancing to address precursors, which is sort of where California's moving. I'd say the most advanced regulatory environment at the moment, mainly focused on drinking water to assess a wider range of PFAS. But there are a lot more PFAS out there than we're currently testing for with conventional target methods.
So if you're just sort of starting out at a site that might have detected some PFOA or PFAS or something regulated in the water, and you're trying to figure out the source and what's going on, what should you be testing for? And do you go to top assay right away, and then do the 1633 on that result, or what should people be doing for their analysis?
Oh, I push that back and say, well, what are your objectives of the testing? Are you to comply with current regulations, or try and evaluate what's really there and find the source of what's there? Because that would lead into, well, which analytical method you would use. If you're trying to say, well, we think most of the PFAS in the water is coming from this plant that's been doing leather tanning or some kind of paper mill, you might first want to go in and look for the regulated PFAS, but then go back with more advanced methods to work out if you can find the precursors that are associated with that industry. What we've been doing for like drinking water supplies is running high resolution mass spec on the drinking water and finding some weird PFAS that are only associated with certain activities to then help the drinking water purveyor work out, well, where does this PFAS that's regulated, like PFOS, PFOA, where does that come from? Because there are these other weird PFAS that are associated with it.
Okay. So yeah, somebody's commenting that this presentation makes it seem like PFAS maybe aren't forever chemicals, but I think it's the precursors that maybe aren't forever, but the per things are forever. Right?
Yeah, it depends how you define it, because a part of every PFAS lasts forever, but the parent molecule may not last forever, but the tail will. So they are forever chemicals as they're not disappearing. But well, this part isn't disappearing, and they're making more of the chemicals that do last forever. So this is only this molecule will never fully degrade. This part will, and it will make PFOA.
Hope everybody thinks Ian's done at 3 so they can start asking him
Yeah, it
questions.
shows up straight into the next meeting. Yeah.
Yeah. So, real quick though, it seems like people are wondering, is there anything happening in nature that is hopeful about the breaking down some of these perfluorinated compounds? And also, is there anything in nature that's sort of preventing or binding up and not having the transformations happen?
I'd say, yeah, there are some publications identifying that PFOS, PFOA are being degraded by bacteria, but they've never been repeated. So there's questions over whether they're credible at the moment. So I think it's more there's some data came out a few years ago, and there's been a rebuttal in the last sort of year or so about the validity of the data. So I personally not seeing an organism that is mineralizing and taking everything to fluoride and CO2 when you think about PFOS, PFOA. Then in terms of binding things up, yeah, if you convert the conditions to anaerobic, you can slow the precursor transformation, but that depends on I mean, if you had a fire training area and you wanted to turn it anaerobic, fair enough. If you had some TCE as well, that would help. But you don't find sometimes anaerobic conditions last forever, as you'll get groundwater intrusion, for example.
Yeah.
So in terms of concentrating, yeah, some plants will concentrate PFAS up a little bit, but that tends to be the shorter chains and the ultra short chains that concentrate in the edible portion of crops, and they accumulate like in wheat and sunflowers and lettuce. The longer chains stay in the shoots and the roots of plants, but there's no mechanism by which the plants are degrading the PFAS, like destroying them. They may engage in precursor transformation, but yeah, I mean, it was known since 1949 that these molecules are extremely robust and were seen as being great construction materials, but people just don't want to be drinking construction materials every day. That's the way it goes.
Okay, so real quick, Ian's going to be presenting on ultra shorts on August 20th. So that's just in 2 weeks, a little less than 2 weeks. So you can learn more about ultra shorts. And then also just one last closing thing. So even though PFOA and PFAS themselves are not being manufactured or used in the US anymore, things that are precursors to them and that can end up as them are still being manufactured and used. Yes? Yes? Ian?
Not necessarily. It depends on the individual companies. The PFOA stewardship program the US EPA brought in 2010 should have eliminated long chain manufacturing. It's just I would be suspicious that firefighting foams are being imported that still contain PFOS from other countries, and there's a lack of sort of regulation and testing of PFOS precursors, but that's only from anecdotal evidence of foams still being imported. PFOS and PFOA are still widely manufactured in other parts of the world and can be in articles that are imported.
Right. All right. Well, I think we're going to have to close that there. There were still a few more questions. And just a reminder, if you did want the LSP credits, you are supposed to type in at least one question. So I'll leave the webinar open for just another couple minutes so people can type, if they want LSP credits and they haven't yet typed in a question, they can just put some question in. And so, but with that, thank you so much to everybody that attended. And thank you so much to Linda Gaines from EPA for presenting on all the historic uses of PFAS and current, a lot of them are current uses. And then also Ian Ross and talking about all this precursors and transformation and all of that. So thank you so much to the presenters and for everybody that attended today. And if you do want the LSP credits, make sure you email me to let me know that you want a certificate, because I don't know. Or you could type that in as your question or your comment. And with that, I think everybody just enjoy the rest of your day. Thank you so much again to Ian and Linda. I'm going to end the webinar now. Okay, bye-bye.